Here we have our robot catapult player. It's powered by a 21 amp hour lithium ion battery. It has two 250 Newton electromagnets that secure it, ready for fire, and it's powered by a 70-pound spear gun band. So to operate, you have to engage the button, bring it down to load. So load the bag, step over it, and fire.
Cornhole is a game typically played at American football tailgates that's fun for the kids and family. So we came up with a new way to play the cornhole game. Our method will automatically keep track of the cornhole game, update score, and you're able to play against a robot player. When designing this game, we came up with two main motivating factors. Firstly, we want this entire thing to be solar powered so it's able to be played outdoors. Secondly, we want the entire system to be able to last at least a minimum of 8 hours, or the length of an average tailgate. The opposing boards are placed approximately 30 feet away from each other. The two teams compete. Both teams throw 4 bags per round. The scoring in cornhole is pretty basic. If one bag lands on the board, it's 1 point, and if it goes through the hole, it's 3 points. The absolute difference is taken between both team scores to determine the round ending score. For example, if the round is over and there are 2 blue bags on the board and 1 red bag, that means blue is up 1-0. Our automated cornhole system requires multiple modular components.
Our power supply is supplied by a 100 watt 18 volt grape solar panel that feeds into a 10 amp Renogy charge controller. The reason we selected this is because it has a 12 volt and 5 volt power supply. That 5 volt power supply powers our 4-inch screen as well as our Raspberry Pi. Our energy source storage is a 21 amp hour lithium ion battery, and then the Raspberry Pi provides that 5 volt source to all of our other components such as the camera. And it supplies 5 volts from the Raspberry Pi is sent to a buck converter that provides the 3.3 volts to our DC infrared sensor for hole detection. We installed a port on the front of our power supply to be able to connect to the robot player. This allows the power supply to recharge the battery and the robot player through a power cable. With all these connected components, our discharge rate is around 0.8 amps. With a 21 amp hour battery, this greatly exceeds our 8-hour constriction. The DC infrared sensor works by means of emitting infrared light on one end and the other side having a photodiode that gets on with that infrared light. When the bag breaks this beam, a signal is sent to the Raspberry Pi indicating that a bag is passed through the hole. With the depth sensing camera, as soon as that signal is sent, the frame is taken and it determines the color that is passing through the hole, assigning points to the correct team. The robot player that we previously discussed, we wanted to allow it to not be exactly dead on to where it would make a score of 3 points every single throw. So we allowed some random movement into the catapult arm to make it a little bit more fair.
This shows a flowchart of our software outline. In the top left, we start when a bag is thrown. As the bag is thrown, the camera continuously scans every 1 millisecond and finds all the contours on the current image and assigns a score to each team depending on what color the contour is found as. The way we find the contours is we first take background images and crop them to the size of the board, and then perform background subtraction and binary thresholding to turn the image into a binary image where only the bags are white and the background is black. This way, it makes contouring much easier to find. If the bag is located in the game space, we check to see if the centroid of the current contour is found to be inside the game space. It checks to see if the laser sensor has been passed, and if it has, it gives it 3 points, and if it hasn't, it gives it 1 point. However, if the centroid is not detected in the game space, there are no points at all. There are 3 scores being kept at once: the current score, the inning score, and the total score. The current score keeps the current running score, whereas the inning score is calculated at the end to determine all of the subtractions to find which team scored and which team didn't per inning, and the total score is the overall score through innings. When the black bag is put on the board to signal the end of the inning, we take the inning score and add it to the total score. Then we go down and we manually adjust the score if needed. Sometimes this is needed due to stacked bags and other things that we cannot possibly figure out with just a simple computer vision software. So after we calculate the game score, we check to see if a player has won, and winning is a total of 21 points for one team. If somebody does win, the score changes from the current score to 1-0 in favor of the winner team, and then it closes and displays a winner sign. Here we can see an example of how the algorithm works. On the left, we have the grayscale background image. We use this to subtract from the current stream to do background subtraction. And then on the right, we can see the thresholded image for binary values for bag detection. This is a live demonstration of how the contours are shown on the image. When the bag is thrown on the board, we can see that red goes to 1-0. And then when the next bag is thrown, it's now 1-1, and then another red bag comes on and it is 2-1. And on the bottom right, we can see what is actually output on the small screen for the scoreboard.
There are a few project limitations that we've experienced while designing our automated cornhole game. One of the main issues we experience is sensing. When two bags are touching each other on the board physically, our program counts it as one contour, and we're unable to distinguish between the two separate bags. Another limitation is when two bags are stacked on top of each other. This is due to the depth sensor not having enough precision to distinguish between two separate bags. Other challenges experienced were the capabilities of components. We had to switch operating systems 3 times, needing very specific cables to make everything work as expected, handling all edge cases of the cornhole in the code. Initially, we were using BLE triangulation. However, we had a parts problem where the part would take over a month to come in, and this wasn't feasible for our project timeline, so we had to switch to a depth sensing camera because that was feasible. So our future directions for this project are the following: accurately detecting several stacked bags, detecting large collections of the same bag color, projectile trajectory tracking, allow users to manually adjust thresholds for lighting before the game starts. In conclusion, we use the Intel Depth Sense camera to detect bags using OpenCV. Image processing is best done in ideal conditions, which in the case of our project were not ideal. The entire system can run for an entire length of a tailgate for more than 8 hours using our power delivery system and solar panel. The Intel infrared stereo camera depth sensing was not as accurate as claimed on the spec sheet, so we were unable to detect stacked bags on top of each other. And another thing we learned was team problem solving skills. We would like to acknowledge the ECE department, ECE Sparkspace, and the Design ECE Central Lab. Also, we would like to thank Dr. Raza for the generous amounts of help with any of the experience we issued.